FloEFD for Solid Edge is a 3D CFD tool which allows for fast and accurate fluid flow and heat transfer simulations directly within the Solid Edge environment. FloEFD is different from traditional CFD tools as it is aimed at mechanical design engineers and not specialized analysts, and there are several unique technologies which make this possible. FloEFD is a unique engineering tool which allows you to increase the productivity and the quality of your designs by front-loading CFD. Front-loading CFD refers to the practice of moving CFD analysis earlier in the design process, enabling you to examine and evaluate multiple design options, ultimately resulting in an optimized product performance and reliability. FloEFD technology can reduce simulation time by as much as 75% compared to traditional CFD tools. Let's see how. One of the headline features of FloEFD for Solid Edge is the fact that it is a Solid Edge embedded CFD tool. On the screen, we have Solid Edge ST9 and FloEFD plugs into the software with its own ribbon toolbar and FloEFD feature tree. Being CAD embedded has several advantages, such as being able to use assemblies natively without the need for export and translation. Boundary conditions are applied directly onto the Solid Edge geometry by selecting faces in the view window. In this instance, we have an outlet flow and an inlet pressure condition. Post-processing is performed in the Solid Edge GUI also. For example, cut plots can be created and overlaid over the geometry. This cut plot shows the velocity distribution slicing through the model. This plot can be probed to determine the mouse position parameter value. The plot can also be animated to sweep through the assembly. A surface plot shows the fluid region colored by pressure. We can see the largest pressure differential around the throttle as this is where the largest blockage to the flow is. Again, the plot can be probed to determine pressures at the mouse position. Flow trajectories show how the flow looks dynamically, and by zooming into the throttle body, this shows how the flow is being deflected and guided down the intake runners. This plot shows the velocity, but any parameter can be visualized. Being Solid Edge embedded means that we can make parametric changes to the model very easily. To study a variant, let's change the throttle body angle constraint from 300 to 320 degrees. The model needs to be run and solved again, but we can clearly see the difference resulting from the throttle position by looking at the flow and cut plots. Being Solid Edge embedded makes variant analysis and optimization very quick and easy to perform. The second key feature is the ability to handle complex arbitrary volume solids using immersed boundary Cartesian meshing. Here we have a motorcycle headlight unit which we wish to mesh. FloEFD handles this complex shape very quickly using automatic or manual mesh settings. FloEFD uses the Cartesian meshing schema, which can be seen here with increasing mesh density levels closer to the volume. FloEFD also has the ability to handle multiple control volumes within a single cell. This cell has fluid, solid, and fluid regions. The mesh can be visualized further by moving the plane to the desired location. Mesh refinement levels can be visualized, and in this example, we have a range between 0 and 4, 0 being the base mesh. Multi-control volume cells can exist at any mesh level. A 3D representation of the mesh can be projected onto the geometry to check for mesh quality and refinement levels. FloEFD is very tolerant of dirty geometry and overlapping components. It handles complex shapes very easily due to the fact that a fine boundary layer mesh does not need to be generated. The third key technology is how FloEFD handles the boundary layer which forms on the surface of a solid. This example is using a heatsink in a wind tunnel to determine the thermal resistance and pressure drop characteristics. There is an inlet velocity of 4 meters per second and a 30-watt volume heat source. Looking at the mesh shows the Cartesian nature again with finer grid cell levels near the heatsink fins. Multi-control volume cells exist at the walls, which is where the proprietary wall function is applied. This allows for coarse meshing at the walls whilst retaining the correct flow and heat transfer characteristics. Looking at the velocity, we can see the boundary layer at the walls and how this grows as the flow moves from left to right. We can see the same boundary layer growth if we zoom out and look at the walls of the wind tunnel also. Here we have the pressure plotted showing the resistance to the flow as the air passes through the heatsink. The CFD predicts a 3.88 millimeters of water pressure drop total. The datasheet for this heatsink has a pressure drop of between 3.8 and 3.9 millimeters of water. The benefit is that we do not require a dense wall mesh and still get accurate results, negating the need to be a meshing expert. The final key feature is the turbulence modeling in FloEFD. In this example, we're going to be having a look at an external aerodynamics application of a subsonic aircraft. A symmetry condition has been used on the domain to reduce the calculation time. By going into the general settings, we can see the options we have available for flow and turbulence. The flight speed and angle of attack can be parametrically defined so they can be used later for an alpha sweep. FloEFD uses a two-equation RANS turbulence model which can be defined either by intensity and length or energy and dissipation. Looking at the mesh from the side, solution adaptive meshing has been enabled and is evident by looking at the increased mesh density in areas of high flow gradient. The mesh around the wing is also refined, especially around the leading and trailing edges. We can see a high velocity along the top surface and lower along the bottom, as we would expect. Turbulence parameters can also be visualized. Here we have the turbulent energy, which can be seen along the top surface and trailing edge. Turbulence dissipation can also be seen the most along the leading, top face and trailing edge where the two streams combine. A surface plot of pressure shows the high pressure below the aircraft, which is what gives the lift. Flow around the aircraft shows the velocity vectors and is useful for determining flow separation or stall conditions. Wingtip flow behavior can be seen, which increases drag and reduces lift. In conclusion, FloEFD has several unique proprietary features which make CFD analysis faster and more accessible to design engineers. Complex geometry handling, without having to worry about boundary layer meshing, whilst being MCAD embedded, makes FloEFD a front-loading CFD tool for engineers and not analysis experts. Flow and thermal optimization earlier in the design cycle means less physical prototypes, more reliable products, and faster time to market.